Everybody. We're talking about sound intensity and loudness today. So you see on the screen there that it says we're talking about understanding decibels. But before we get into that, I want to talk about a couple of aside things. One, in the bottom left-hand corner of the screen here, we have some, I'm going to be looking off to the side so I can see my screen while I'm looking at you. We've got this idea of a speaker, and at a position A, B, and C, away from that speaker, say 1 meters, 2 meters, and 4 meters, we might want to think about how would the intensity change? The intensity of sound is measured as the amount of watts per meter squared that smack into an area at that position. So if we think of sound as traveling a distance from a source outwardly, it might be useful to think about how that energy spreads out as it ripples outwards. And I think the best way to think about that is probably to simulate water ripples, because that's something that we're familiar with. So I've got here a simulator for a ripple tank. It can simulate different kinds of waves, but in this case, we're thinking about sound waves. And I want you to think about this dot in the center as being kind of like a speaker. This speaker is able to pulse. It's pulsing right now in a pure tone, a specific frequency, and it's making an over and over wave pattern. It's repeating. And instead of conceptualizing this as a ripple on water, let's think about it the way sound travels outward from a sound source. Sound travels as like a 3D ripple outward as a sphere, an ever-growing sphere. So while it's hard to depict a 3D form in this kind of a medium, like this two-dimensional medium, we can think of this as an expanding sphere. Think of each of these rings as a bubble that's getting bigger and bigger and bigger, a sound bubble, if you like, where each of the bright bands represents compression regions and each of the dark bands represents rarefaction regions of expanding sound ripples that go out spherically. So I want to take a look. I think we had this once before. If you bothered to take a look at some of the extra videos. Where are we here? Oh yeah, we had a little visualizer once upon a time. So I'll just show this really briefly. Oops, my cursor's in the wrong screen.
And sound, well, that's just another change in air density, a traveling compression wave. So Schlieren visualization, along with a high-speed camera, can be used to see it as well.
Okay, so we had this idea once. Oh, there's a little ad there. We had this idea once upon a time that sound waves really are these density ripples, these compression rarefaction ripples, and they're going outward from a sound source. So we have this simulator here, or you could look at a Schlieren visualization and you could get a more real view of it. But in either case, we're talking about ever increasing sound ripple sizes. And so at 1 meter away from a sound source, the intensity would be spread over the energy would be spread over a small sphere of a ripple. Whereas at 2 meters, it would be spread over an even larger spherical ripple. And at 4 meters, the energy would be spread out over an even larger spherical ripple. And what we're saying here is that the energy is getting spread out, not created or destroyed, but spread out over ever increasing ripple sizes, but spherical ripples, right? Now that's one idea we want to talk about today. Another idea is this idea of decibels. And decibels is a way of talking about loudness. I'm going to be intentional about my use of the word intensity and my use of the word loudness, only for the purposes of this conversation, because it makes it easier for me to be specific in that way. So intensity I'm going to talk about in terms of watts per meter squared of energy that smacks into a surface as that energy gets radiated out from a sound source. When I talk about loudness, I want to talk about decibels. Now, decibels is a comparison of one intensity to another, and it's really a comparison measurement. So in the case of human decibels, and I'll get to this later in more detail, but in the case of human decibels, we measure all of our intensities relative to the quietest sound that the average human can hear. And I'll talk about that more. But maybe before I go and talk about the rest of this slideshow, it would be useful to pull up a quick video. It's about 4 minutes long, and it's worth watching just to talk about the idea of loudness. So let me pull this down. I'm like, ooh, that's so hypnotic. And I want to pull up this PBS Digital Studios video, It's Okay to Be Smart. I'm going to crop myself out of this picture. Here we go.
If I had a machine that allowed me to suddenly transport myself elsewhere, the air filling the vacuum where I used to be would collapse with such force that it would burst eardrums and cause nausea to anyone standing nearby. Teleportation may sound like a cool idea, but because of sound itself, it's a pretty dangerous proposition. A sound wave is mechanical. It needs a medium to travel through. Now, right now, the wave created by my voice is wiggling the air back and forth, creating areas of higher and lower pressure. When we talk about how loud a sound is, we're really talking about the intensity of that pressure wave. The louder the sound, the more intense the wave. Unlike ripples on a pond, sound waves move out from a source in the shape of a sphere. And just like a bubble gets thinner as it gets bigger, the farther we are from the source of a sound, the less pressure there is on a given area of the sound sphere. This means that if we move twice as far from a sound, we'll be at 1/4 the intensity. The smallest sound pressure wave we can hear vibrates our eardrum less than the width of a single oxygen molecule, yet we can comfortably hear sounds 1 billion times more intense. Hearing has the widest range of any of our senses by far, so we need a wide scale to measure it. To do that, we use decibels. dBs are logarithmic. Something 10 decibels louder is 10 times as intense. 30 decibels, 1,000 times as intense. Our threshold for pain comes at sounds 10 trillion times more intense than the quietest sound we can hear. Highway traffic is about 90 decibels. Shots can be higher. In 1883, the island of Krakatoa in the South Pacific erupted, sending ash nearly 17 miles into the atmosphere with a force 4 times more powerful than the Tsar Bomba, the most powerful nuclear weapon ever detonated. At nearly 180 decibels, this explosion shattered eardrums 40 miles away and pushed a wave of air around the globe 4 times. Imagine hearing this only 3,000 miles away. Get close enough to that, and it'll be the last sound you never hear. But there's an upper limit to how loud a sound can be, and hint, it's not 11. Sound waves push air together at their peak and leave low pressure in the valleys. Now, once this part has reached a vacuum, the sound can't get any louder. Push the wave any harder than 194 decibels, then it distorts and heats up. It's moving faster than the speed of sound. Now we can go higher, only then it stopped being a sound and has become a shock wave. NASA's Saturn V rocket was capable of shooting out 7.5 million pounds of space fire thrust at 200 to 220 decibels. That's enough pressure to ignite grass 1.5 kilometers away and kill everything within a few hundred meters. For space shuttle launches, NASA dumped water at a rate of 900,000 gallons per minute into a pool underneath the launch pad to keep the sound waves from literally ripping the shuttle apart. Of course, planets with more dense atmospheres like Venus or Saturn could sustain more intense sound waves and even higher decibel levels. Makes me wonder, what would a lightning storm on Saturn sound like? In fact, I'd like to find out. Stay curious. Could actual human clones really exist? Well, hey.
Whoa, where did that go to? All right, let me bring me back again. There I am. All right, let me pull this out of the way and get on to my next bit. So he explains that pretty well, but I got to get onto the slideshow, unfortunately. And if you want to go back and watch the video, by all means, remember, anything that I use in videos are linked on my website. We're on topic 5 right now on the website. So there are a few videos there. I'm not going to watch all 3 of them. Loudness and pitch is just sort of a friend of a friend standing in front of a blackboard talking about some ideas that we're talking about right now. And then C is somebody that I don't know at all. She has a lovely YouTube channel that kind of talks about like the philosophy of math, but she talks about what logarithms are, and logarithms are so connected to decibels that I thought that I would include that. It's 9 minutes long, and if you like sort of math philosophy and people rambling and talking about math philosophy for a while, she's a good listen. She's worth listening to. I really like the channel. It just doesn't quite fit with my lesson, but I would encourage you to watch it and check it out. She's got a lot of views and a lot of likes. All right, let me pull up my slideshow here. And just to give some context, let me deal with myself properly. There we go. I'll take my face off because I don't like having my face on there anyway. To give some context in terms of decibels, because we're going to get to decibels, our average conversation is about 65 decibels, if you can see that on the screen. Car passing, about 75 decibels, if it's about 50 feet away as it drives by. And a big truck is about 85 decibels. Okay, so if we're walking along in our everyday life, there's a picture of somebody walking the dog there. These are some of the decibels that we might encounter. Now, there we go. When we're talking about this kind of analysis of sound energies, it's going to be useful to go back and talk about power and watts, because we're talking about how much energy is put out by a sound source per second. So we haven't thrown out the idea of what power is. It's the exact same definition as what we've had before. Power, or sound energy, gets radiated out by a sound source over units of time. We call that watts. Same as we did in any other unit in this course. Oh, come on. There we go, an equation. So again, we've got this idea of power equaling the amount of work done divided by the amount of time. I hate the format of this equation. Can you please cross out the capital letter W and replace it with delta E, like we have kept on doing? And this T in the denominator, I just took this straight out of a textbook. This T in the denominator should be delta T. So really, power is delta E over delta T, just like it always has been. Please write it that way. And we're talking about units of joules of sound energy per second. And don't ask me how joules of sound energy is different than joules of thermal energy. A joule is a joule. It's just a unit of energy. It's not that it's a different kind of energy. It's an energy that was released by vibrations that we call sound. Okay, so the power of a sound source is the amount of joules per second that sound source is putting out as it produces spherically radiating out sound waves. Somebody asked me earlier this week, are we going to only consider the ideal case? And yeah, we are. We're only going to consider sound waves that radiate out spherically. I know that's not quite true, because if you put a speaker on the ground itself will get in the way. Obstacles in a concert will get in the way. I mean, that's the whole point of having acoustic paneling in a recording studio. So we are going to totally idealize this as usual, and we're going to make it be spherically radiating waves, like I introduced at the beginning of this lesson. Again, to sort of put this in perspective, we talk about, and actually in the video, he talked about the kind of breadth that we have in our sensitivity to sound. And this is a historical one. You can see a super old snapshot of Google Maps there on the screen. But I took this screenshot ages ago. I can't even remember when it was. I can't see a date on there, but it really was quite a while ago. And the idea was put forward, and you can read it through in the red. The physicist Alexander Wood once compared the range from loudest to the quietest noise that a human can hear, the noise that can be made, to the energy received from a 50-watt light bulb situated in London when standing 5 feet away, to the energy received by someone standing in New York City. Like, that is a huge breadth of power. When we think about the amount of power that is put out by a 50-watt light bulb, and we're talking like the old-fashioned incandescent light bulbs, so a light bulb that might be in like a lamp or something, the amount of energy that you and I can observe has this huge breadth of energy, of sensitivity. We can hear really, really quiet sounds, and we can hear really, really loud sounds. Really, really quiet sounds, so quiet that our nerves are just barely being stimulated by the vibration of our inner and middle ear, and so loud that our ear mechanisms actually get torn apart by the vibrations. That's the upper end of what we would consider to be a loud noise, the pain threshold. Oh, here we go. So energy at a distance, for a source that radiates energy, the energy spreads out as it travels. And I'm proposing that we talk about it spreading out spherically. And actually, that's kind of what light does too. Think about light radiating out from the sun. Don't we think about the light radiating out from the sun as radiating out spherically from this like point source that we consider as the sun? It goes out like light bubbles that ripple outwards away from the sun, right? And the intensity of that light would get less and less and less and less and less as you get further from the sun, which of course is a reason for why stars are so dim compared to the sun, because the light bubbles that have been rippling out from those stars are so much more thin and spread out than the light ripples that are coming from our local star, the sun. So here we have like this model of a speaker sitting on the ground, and I have like a hemisphere, a semi-sphere that's radiating outwards from this source. Of course, I know that the ground itself would distort the shape of that sound bubble, but we're going to pretend, for argument's sake, that sound bubbles, regardless of the surroundings, go outward from the sound source in a sphere. And I know that totally negates the purpose of having those cone-shaped diaphragms inside of speakers that are trying to direct the sound forward, but I told you we're making a simplification. So intensity is measured in power per unit of area. And so that would mean that there is a certain amount of power, watts, per meter squared that power gets spread out. And you can see in the illustration, there's a little area here, and this area here is a patch of that sphere. And so we could talk about how many watts of power are hitting this patch if the patch was measured in meters squared. So intensity of sound, a sound wave, as sound spreads out. This is so weird doing a slideshow like this and not having faces to look at. Just an FYI, I have a pink stick-it note sitting just below my camera with a smiley face, and I'm talking to the stick-it note right now because it makes me feel like I'm talking to somebody. And incidentally, the stick-it note has a smile and little glints of reflective glare on its eyeballs. It's kind of anime looking, and it's keeping me company, and I'm pretending that it's my student right now, just so I have somebody to talk to. It's smiling, by the way. All right, so the intensity of a sound wave drops off as the inverse square of the distance from the source. So we think about another inverse square law that we've seen before, and you're probably thinking of gravitational field intensity. And this is where I look at this yellow stick-it note in the top right-hand corner, and what we're talking about is the intensity gets spread out as a power measurement, the power that gets emitted from the power source, being divided over or spread over the surface area of the sound bubble. So we talk about it as power divided by area. And so I'll talk about this intensity as being the power of the source divided by 4 pi r squared. And if you remember your geometry, 4 pi r squared is the surface area of a sphere. So it didn't come up by accident. We're literally talking about the amount of power from the source being spread out over a surface area of a sphere that represents the spherical sound ripple or sound bubble that's coming out from the power source. And the r is the distance away from the power source that we are when we're measuring that intensity. So if you're 1 unit of distance away, 1 r away, the power will be spread out over 1 unit area. If you're 2 r's away or 2 unit distances away from the sound source, your power will be spread out over 4 units of area. And at 3 units away from the power source, we're talking about spreading our power out over 9 units of area. And that represents an inverse square law. And where that inverse square law comes from is the idea that the power is being spread out over ever-increasing spherical ripple surface areas. Fair enough. I don't know how much more to say about that, but that's where the idea comes from, and that's the mathematical relationship. So we've got an expanding ripple, and this expanding spherical ripple has an intensity across that whole surface area, where the intensity is a measurement of the amount of power that it started with at the source divided by the surface area that the ripple now possesses. So intensity of the same source at 2 different distances. We might want to compare 2 different intensities. And if we were to do that, we could do a little bit of math like this. Now, I feel like I want to minimize what's on my screen right now and just pull it off to the corner for a second because I don't want to get lost in PowerPoint. This is one of these things where slideshows easily mystify people. You just throw a whole bunch of math at people and expect that they're going to understand what the heck is going on. So I want to just take a quick digression here and do this math on paper just so people can see where this math comes from, because I really hate mathematical things. I mean, I do. They impress me, but just to make sure that we know where we're at with this. And is my camera focused? Yeah, she seems to be. All right, so if I'm saying that intensity is equal to power divided by 4 pi r squared, in other words, power of the source spherical ripple area we're talking about how much power there is per meter squared of spherical ripple. Let me get this screen bigger. There we go. Bring it a little bit bigger, and maybe I'll bring that guy up on top so we can have it in the corner. All right, so we've got, oh no, make this rectangle bigger too, really maximize our workspace. All right, so we've got intensity equals power over 4 pi r squared. I want to compare two different intensities at two different positions. So I'm going to declare that there's an intensity 1 that would occur when the power from the source gets spread out over a spherical bubble that would be 4 pi r1 squared. And there would be an intensity 2 relative to the spread of power spread over a surface area that would be equal to the power that started at the source divided by 4 pi r2 squared. All right. Now, in terms of taking these two equations and bringing them together to make one, I'd like to bring them together as a ratio. And I think I'd like to do I2 divided by I1. Oops. In other words, if I call this equation 1 and this equation 2, I just took equation 2 and I divided it by equation 1. So I2 over I1 would be equal to, let's see this, P over 4 pi r2 squared divided by P over 4 pi r1 squared. And if it makes it easier to see, I'll put a bracket around the numerator and a bracket around the denominator. Now, whenever I have a fraction divided by another fraction, I know in my heart of hearts that I2 over I1 would be equal to, remember, you take the first fraction, P over 4 pi r2 squared, and then you multiply it by the inverted second fraction. So I invert and multiply. So 4 pi r1 squared over p. And for those of you like me that like to cancel stuff out, immediately I say, hey, pp, get out of here. Oh, pi, get out of here. Oh, 4, get out of here. Lots of canceling happens right away. I can't cancel the r's because they're not the same r. I want to make sure that we understand what we mean by these two r's. We mean that we're talking about an intensity that's occurring as sound spreads out at 1 unit distance away, sorry, one r away, it would be spread out that much. But if I keep on going outwards, it would be spread out, the intensity would be spread out over an even larger area. Okay, so we have a small area here at R1 perhaps, and we have a large area out here at R2, if that was the case. Okay, a lot of times people use R1 as the close distance to the sound source and R2 as the far distance to the sound source, but it actually is arbitrary as long as you're consistent about your labeling. So we go back to this and we say, okay, we've done some canceling. I2 over I1 equals, oh my gosh, what a canceling mess. R1 squared over R2 squared. And actually, you know what, that simplifies things a lot. It's like an algebraic miracle. That's where that little equation comes from in the yellow on the screen there. So if I pull this image up bigger again, let's take a look at the question. It says if the intensity 3 meters from the source is 2 watts per meter squared, we'll give ourselves some givens. One of the intensities is equal to 2 watts per meter squared. And that was at an R value of 3 meters. What's the intensity of the sound at 10 meters? Well, you know what? If this is 3 meters and I'm going to be talking about 10 meters, let's call that I1 and R1. We'll call it I2 with the intensity. That's what we're looking for at an R2 value of 10 meters. I think it's at 10.0 meters. Sorry, we'll keep our 3 sig figs. Bad me. We'll use our equation. We say, okay, so I'm looking for I2. I'm going to say I2 over I1 is equal to R1 squared over R2 squared. I'm going to cross multiply and bring that I1 up the other side. I say that I2 is equal to I1 times R1 squared over R2 squared. By the way, as I'm doing this, I want to point out, because I've had people ask me this in the past, is it a mistake that you have I2 on the top and I1 on the bottom, but R1 on the top and R2 on the bottom. It's not a mistake. Go back and look at the derivation with that invert and multiply thing. That was a correct result. Okay, so let's make sure that that's out of the way, because I've had so many people think I'm making a mistake or a typo. Go back and check the math. Okay. All right, we sub in our values. I1 is equal to 2.00 watts per meter squared. Let me shrink this down just a little bit so I have some space. Times R1 squared, which was 3.00 meters. Don't forget to square it. You'll be sorry. Well, you'll just be wrong, and maybe you won't be sorry. And R2 is equal to 10.0 meters. We'll square that as well. So you could do the math. 3 squared is 9. 9 divided by 10 squared. 10 squared is 100. So 9 divided by 10 is 0.09. Sorry, 9 divided by 100 is 0.09. Oh, let me pull up my calculator. 2 times 9 divided by 100, 0.18. 0.18 units are watts per meter squared. That would be in the intensity that you find at the 10 meter mark away from this particular power source. So you don't even need to know what the power source is. You notice that the power's canceled out. It was the power at the source, but I don't need to know it. Like if it was a 100 watt speaker, I don't need to know that. As long as I have an intensity meter, and an intensity meter that measures watts per meter squared is something that you can download for your phones these days. I mean, you used to have to buy them in the store. I actually have an intensity meter sitting in our classroom. It's super old. It looks like something from original Star Trek. I'm sure that at some point it looked like it was from the future, but now it looks like an antique. And I think it's kind of cool. I keep it around only for that reason, because the battery's corroded out the inside of it and it doesn't work anymore. But I think it's kind of neat that there was like a whole separate device for this. And these days people would usually use like a small, use their phone and use it for multiple different things. All right, I want to go back to the slideshow now. So you minimize that puppy, put that down in the corner, and go back to the slideshow. Whoa, all right, whoa, so many things. All right, the next thing I want to take a look at is this idea that this inverse square law is going to mean that the intensity drops off really quickly. And you remember that that was the case with gravitational field intensity for universal law of gravitation. But anytime you have an inverse square law, if you have a squared value, a squared r value in the denominator, every time you increase that r value in the denominator, because it's squared, it's going to cause this huge drop off in the magnitude of the overall expression. So yeah, the further you get away from a sound source, the quieter it gets, and pretty fast. Like, that's why whispering works. You can whisper in somebody's ear, right up close to their ear, but people only a meter away won't be able to hear you, because as you get further and further away, it drops off, or the intensity drops off as an inverse square law. And I mean, I don't know how better to explain that other than whispering. That's the lived experience that a lot of us have. It's a small intensity, which is enough when placed right up to somebody's ear, but it drops off so rapidly that people almost right next to you, next seat over, aren't going to hear it. I want to pause for a second here. I want you to read through this red. Give it a good read. I'm going to stop talking. I'm not even going to pause my video. I'm just going to let the video play for a minute. If you want to pause, pause it. All right, that's as long as I'm willing to stay quiet for. I want to take a look at this and figure out what it means, okay? So there are a few different ways that we could go about talking about this, but I want to do a little bit of math talk for a minute, because if you're somebody who has taken math and talked about logarithms, this is something that you're going to feel very comfortable with already, hopefully. But if you're somebody who hasn't talked about logarithms yet, this is going to be something that's quite new to you. So I'm going to pull up my lined paper again, do a little bit of flipping, and I just want to play around with numbers, because I think that there's some value in thinking this out loud. I know we're half an hour into the video, and you're welcome to skip past this if you want to, but I'm going to play around with numbers for a minute, okay? I know that if I write something like 1,000, that's the same thing as 10 times 10 times 10. I also know that if I write 10,000, you could probably already say it out loud. That's going to be equal to 10 times 10 times 10 times 10. And we have this shorthand where we say, oh, well, that means that we have 10 to the power of 3. Or that means we have 10 to the power of 4. And without a whole lot of thinking, I bet you could see where I'm going with this. 1, 2, 3, 1, 2, 3. This would be, do I even have to write out all those 10s? Nobody does that anymore. You get up to the grade 11 level, you say that's 10 to the 6. Not a problem. I'm not even going to waste my paper on that one. I know that it's 10 to the 6. What about this? What if I want to undo it? What if I have 10 to the power of 21? And I'd like to figure out what number that's going to represent. You know how many zeros it's going to be, right? Can you see it? It's going to be 21 zeros, isn't it? 1, 2, 3. 1, 2, 3. 1, 2, 3. Oh my gosh, why did I do this to myself? I'm going to run out of space. 3, 6, 9, 12, 15, 18. Did I get 21? It's a big number. I don't even know what 10 to the power 21 is. I don't have a special name for that one. I forgot that one. If I ever knew it, I don't remember it right now. And you could look it up if you want to. I know you probably are right now. You're pausing the video and looking up what 10 to the 21 is called. It's not trillion, more than that. Anyway, it's a big number, honey. That is a big number. And people use it. I mean, these are things that come up in astronomy. These are things that come up in chemistry. We know that these big numbers exist. We've got to be able to deal with them. What about this? What if I tried this route? If I had log of 1,000. By the way, for those of you that have taken senior math, you know it's actually log base 10 that your calculator defaults to. But let's just see what happens if I do log of 1,000. If I do log, my calculator makes me put 1,000 and then log. 1, 2, 3, and then log. Turns out the answer is 3. Let's see if we can develop a pattern here. I'm going to take my 10,000, log of 10,000. And right now, by the way, I'm just teaching about this new button called log. Where's my log button? Right over there. So 10,000, and again, on your calculator, you might type in log and then the 10,000. It actually is going to be the same pattern as how your trig buttons work. So if you do like the angle and then sine, then you're doing what I'm doing. But if you do sine and then the angle, like sine 45, instead of 45 and then type the sine button, it's the same pattern of button keying. You try it out. Make sure that your calculator works the same way or you get the same results as I do, okay? So 10,000 and then log, give me 4. Now, if I relate this back up to what was happening at the top of the page, see up here? 10 to the power of c, 10 to the power of 3, 10 to the power of 4. We get sort of an idea that maybe these two ideas are connected. What about this? You make a prediction in your head. If I do log of 100, what do you predict it's going to be? Make a mental prediction. You don't even have to write anything down at this point. Try it out. 100, log. Did you guess right? It's 2. Now, the people that I know in math are going to hate it if I do this. But what if log just tells you how many times you would have to multiply 10 by itself, that's the base, to get 1,000? Does that make sense? Let's try this. What if I had log of 10 to the power of 5? So 10 to the power of 5 did it the wrong way. 10 to the power of 5 equals 5. Now, a student a while back said, is that kind of like log is inverse of 10 to the power of? And that kind of made me laugh. Does like log undo a 10 to the power of and like get you back to the number you started with in the exponent? I guess so. I guess that's kind of what it's like. It's almost like it's a 10 to the power of inverse. Like sine has a sine inverse. There's log and there's 10 to the power of, and log is kind of like an inverse function of 10 to the power of. That's one way of talking about it, okay? What about this? What if I had log of 17? I chose 17 because 17 is a prime number and I love prime numbers, which is so fun. Let's see what happens. 17 log. Now, it's 1.23. I'll give myself as many decimals as I can here. 1.23044891. That's the whole thing that comes up on my calculator. And people say, well, so what does that mean? What have we just done by logging 17? Let's see. If it follows the pattern, could we do 10 to the power of 1.23044.821? And what do you think the answer is going to be? Oh my gosh! It's pretty darn close to 17. In fact, I would say that 10 to the power of 1.23044 is pretty much equal to 17. And the only reason it's not exactly equal to is because I rounded it off. I should have kept on going, but I don't have infinite decimal places on my calculator. That's pretty impressive. What about this? If I had log of 23, love those prime numbers. Let's see. 23 logged 1.3617. All right, let's see. 1.361727836. We'll type it in just for argument's sake. 10 to the power of 1.3617 and I'll type it into my calculator. 10 to the power of 1.361727836 equals beauty 23. This not 23 factorial, just 23. That is awesome. That's what log is for. Log is like the opposite of 10 to the power of, if you like. In other words, if I have log of 23, it's telling me what I would have to have 10 to the power of to get back to 23. All right, I feel satisfied with that. I feel like I sort of get what the log button is for. Now, if you want to go back and explore what logs are all about, don't worry, I've got a place for you to look at that as well. And of course, you can always look it up on the internet as well to get more information about logs. Unfortunately, this is the one lesson in this course that kind of comes before you learning it in math class. And you're going to learn all about logarithms in your next math course. If you haven't reached up to grade 12, you're going to learn about it in grade 12 most likely. Or maybe you'll learn about it in grade 11. Gosh, I always forget what grade it is. But it's not necessary for you to have learned about logs before you land on my doorstep. So I always have to reteach logs. All right. So decibels. Let me pause it here. Let me allow you to read. I'm going to pause talking for a minute. All right, I'm back again. If you need to pause it again and go back and read it, you can. So the idea of a decibel is that a decibel isn't really an intensity. It's a measure of loudness, but it's a comparison of two noises. It's actually a comparison of two intensities. And we're actually not going to use pascals. We're going to use watts per meter squared. So let's talk about the history. And gosh, I hate to ask you to pause it again, but pause it and give her a read. Oops. So we've got this idea of decibels, originally having the name bell, talking about loudness, and it had something to do with the comparison of intensities. But the bell was just enormous. It turned out that it was just too unwieldy in terms of its size, so it gets scaled back to being the decibel. Okay, so it gets the symbol dB, lowercase d, capital B. And actually, if I can minimize for a second here, most people don't even write it as lowercase d, capital B. They write it as lowercase d and then Greek beta with that sort of descender there. Okay, so back to the slideshow here. All right, so I want to talk about calculating, oh my gosh, laggy on my slideshow. I want to talk about, there we go, calculating decibels. So this is the formula for decibels. And I think it might be useful for me to try and share my screen between my handwriting and my slideshow here for a minute. And this is one of those situations where in a classroom, I'm dancing back and forth between my slideshow and my whiteboard, but I can totally do it. I got this little space down here at the bottom. So we write it as a Greek letter beta, and that's equal to 10 times log, that log button I was showing you before, of the ratio of intensity 2 divided by intensity 1, where intensity 2 is often the louder of the two intensities, decibels. And you can write it as the word decibels, or you can write it with the symbol, lowercase d, capital beta, decibels. Now really, decibels aren't a proper unit. They're actually just sort of a placeholder to let you know that you compared two intensities. Because if I go back and I look at this formula, remember intensity 2 has units of watts per meter squared, and intensity 1 also has units of watts per meter squared, and those two watts per meter squares are going to cancel each other out. So really and truly, there's no other place to get a unit from. So the decibel placeholder is really just there to give people the information that two intensities of sound have been compared to each other. And so we have this idea of a decibel as being a unit. It's not really a unit in its truest sense. It's a placeholder to let us know that two intensities have been compared. All right, let me biggie size this again. So in this example, we've got, what's the intensity difference, because that's what a decibel is, between a 3.5 and a 0.02 watt per meter squared intensity. So 3.5 watts per meter squared as compared to 0.02 watts per meter squared. Well, I take my formula, and you notice the way that I typed this up, I didn't include the units of watts per meter squared. Really, that's just because I was having a hard time getting the superscripts to work, I think, when I made up this slideshow. But that's okay. You can put it into your calculator, type in the 3.5 divided by 0.02 logged times 10, and you end up getting 22.4 decibels as the decibel difference in intensity. So that we could talk about there being a loudness difference, if you like. We want to switch from the idea of intensities. We use intensities to talk about the watts per meter squared measurement in this course. That's how we're going to phrase things so that we can be consistent. And we'll talk about loudness as a description of that decibel difference between those intensities. So the loudness difference between these two intensities is 22.4 decibels. Decibels being a comparison of intensities. So example 2, if the intensity of one sound is 100 times greater than that of another, then we could say, okay, well, I2 would be 100, I1 would just be 1. So the ratio of I2 divided by I1 would just be 100, because 100 divided by 1 is 100. And of course, the watts per meter squared cancel out anyway. So log of 100 is 2. You notice we saw that pattern once before. That's 10 to the power of 2, and 100 is 10 to the power of 2, and log undoes the 10 and brings the 2 out. So 10 times 2, 20 decibels. There would be a 20 decibel loudness difference between those two intensities. Okay, we could go through other silly examples. Maybe we could have a 2-to-1 ratio. Now, in this case, I've chosen more realistic watt per meter squared values for actual sounds that humans might hear. So we have a 4 times 10 to the power of negative 12 watts per meter squared sound compared to an intensity of 2 times 10 to the power of negative 12 watts per meter squared. 10 to the power of negative 12 watts per meter squared. Like, that's actually a scale of sound intensity that you and I could listen to. Oops. So again, we've got the same formula. We sub in our intensities. Oh, I got the superscripts to work that time. Oh well, anyway. Still don't have the units. The units are going to cancel out. We should be including our units in the calculation, so bad me. And you end up getting, because it's still a ratio of 2 to 1, it reduces down to log of 2. And again, this is a weird one, because log of 2, well, 10 to the power of what, right? Would end up giving you 2. That's what the log button is for. You don't have to guess. 10 to the power of 0.301 would be equal to 2. And I get 10 times 0.301, so 3.01 decibels is the loudness difference between those two actual realistic intensities. All right, quick little thing. Let's read through this. Question A, if the sound intensity of an explosion 20,000 meters away, so notice that's 20 kilometers away, is 1 times 10 to the power of negative 12 watts per meter squared, so a realistic sound intensity, what's the intensity of the same explosion that's 0.005 meters away? Notice that that's half a centimeter away. So like if the same sound happened in your earphones, this is a cartoon at the bottom of the screen of kind of the old layout of iPod when it was a dragging wheel. That's the first iPod I had. It was awesome. I liked that iPod a lot. All right, so we're going to compare the intensities between these two sounds. And here I want to give myself a writing surface. So I'm going to pull this up into the corner, give myself a fresh page. Where the heck did I put my phone? Pull that up. Don't feel shy about fast forwarding until I get to the spot where I'm actually teaching. We're 47 minutes into this video. Man, this guy's teaching a long time. All right, so if the sound intensity of an explosion 20,000 meters away, so I'm going to call that an R value. R is equal to 20,000 meters. And it actually says 20,000.0 meters, just so we can emphasize sig figs, I suppose. And the intensity is equal to 1.00 times 10 to the power of negative 12 watts per meter squared. What's the intensity of the same explosion 0.005 meters away? So I'll call that one R1. I'll call that one R2 and I2, the farther away ones. R1 was equal to 0.005 meters away, half a centimeter. And we want to know how intense that would be, right up inside your ear. So imagine there's two people, one that's 20 kilometers away, and the one that's like right on top of this sound. It's being played in their ear. All right, so our equation, you can see it in the bottom right-hand corner of the slideshow, is, you know what, I'm looking for I1. So just a quick math thing. If you've labeled things as I have, just remember that if you invert the left-hand side, you can also invert the right-hand side. Whatever you do to the left, you can also do to the right. So if I have an equation like this one that has the format of one ratio equal to another ratio, and I've already set up my 1 and 2 indices, I could invert I2 over I1 to be I1 over I2, and that's okay so long as I also invert R2 squared over R1 squared, if it's a simple ratio equals another ratio. You could try that for yourself. I mean, see that it works with math. I love this kind of math stuff. You know that 1 over 2 is equal to 2 over 4. And if I invert the left-hand side so that it gives me 2 over 1, then I can still put an equal sign there as long as I invert the right-hand side to be 4 over 2, right? Anyway, math. Okay, back over here. Let's sub in our values. I1 over I2. I wanted to get I1 all by itself, according to my givens. So I2 times R2 squared over R1 squared. Subbing in my values. I2 is 1.00 times 10 to the power of negative 12 watts per meter squared. R2 was equal to 20,000 meters. Don't forget to square it, divided by 0.005 meters squared. And I gotta pop this into my calculator. Boy, I never use my phone as a calculator, so I hope that I can get all my numbers in properly. Double check my work, okay? 1.00 times 10 to the power of negative 1.00 times 10 power of 12 negative equals, okay, good, times 123 squared divided by 0.005 squared equals 16. All right, so I get I1 equals 16 watts per meter squared. All right, cool. Oh, by the way, the units, meters, cancel out over there. So yeah, I am left with watts per meter squared. All right, so that's my intensity. Find the intensity, or find the decibel difference is part B. So this was part A. Part B on my slideshow is find the decibel difference between this value here, I1, which is a big value, compared to I2, which was 1.00 times 10 to the negative 12 watts per meter squared. Oops, this was I2. No, this was I1. Yeah, I1. All right, so I say for B, the formula goes decibels is equal to 10 times log of I over I decibels. In this case, and I said this earlier, it's often fruitful to just talk about the larger value as being in the numerator and the smaller value as being in the denominator, just because it will give you a positive value for your decibel calculation. You can try the reverse and you'll see what happens. I sub in my values, 10 of log I1, 16 watts per meter squared, divided by I2, which was 1.00 times 10 to the power of negative 12 watts per meter squared. And yeah, I know, the units are going to cancel out. Boom, boom. Why bother? But you have to. Decibels is equal to, I hate to do this, but I really hate using my calculator on my phone. I guess I gotta do it because my other calculator's battery died. What a pain in the butt. How do I put this on screen for you? There we go. All right, so 16 divided by 1.00 times 10 power of 12 negative, close parentheses, equals, press log, times 10 equals, I hate this logic sequence. Anyway, it's 132.04 decibels. And I could round that off if I wanted to. Remember that I had 3 sig figs, so approximately 132 decibels. I feel pretty good about that. So the decibel difference between these two intensities is 132 decibels. Go back to my slideshow for a second here. Maybe I can just scroll to the next bit. So at stage C, it says, based on the results from A, would the 0.5 centimeter listening distance cause you pain, given that the human pain threshold is 1 watt per meter squared? Well, yeah, if the human pain threshold is 1 watt per meter squared, 1 watt per meter squared is definitely less than 16 watts per meter squared. I mean, oh my goodness, that's destroyed your ears. You're not able to hear anymore. You're well past the pain threshold. And then as a point of reference, I'm going to ask you to write this down. Put this in a special place, okay? So some people call this I0. I naught, the British might say, is equal to 1.00 times 10 to the power of negative 12 watts per meter squared. And this is a special value. This is the quietest sound that the average healthy person can hear. So I'm just going to call it the quietest sound we hear. And the reason this is important is because we wanted to have a concept called a standardized decibel. And since human hearing isn't really standardizable, we just said, okay, like on average, this is the quietest we can hear. So we're going to use this as the basis of comparison for all of our decibel calculations when we set up stereo systems or whatever. We want to talk about decibels for humans. We're going to use this as the denominator intensity for that beta calculation. So every time I do the decibel calculation and I want to talk about a standard decibel as opposed to a decibel difference between two given intensities, if I want to find a standard decibel, I'm going to use the equation 10 times log of intensity 1 over intensity 0. I'm going to call this intensity 0 from now on, or intensity naught, or I'll just call it the quietest sound we can hear, decibels. And every time I calculate a standardized decibel, I'm going to use 1 times 10 to the power of negative 12 watts per meter squared in that place right down here in the denominator, that I0 position, for my calculation. So whatever that intensity 1 is, I'm always going to compare it to I0, which is equal to 1 times 10 to the power of negative 12 watts per meter squared for a standard decibel. Okay, and that's going to show up in your homework as well. If it asks you to calculate decibel for a particular value or particular intensity, you're going to use this for a standard decibel. But if it gives you two intensities that you're comparing, then you're going to have to use an I1 and an I2, those two intensities, to compare an intensity difference. Or sorry, a decibel difference rather. Let me just go on to the next page. I'm getting lost with my mouse here. Too many screens going at once. Can I ask you please to just take a second here and read this screen? You can pause right now. I'm going to keep on going. So the idea here is that although we do have some safety features built into our earphones, or sorry, into our phones or our iPods when we listen to music, like a lot of generations, this whole idea of perpetually having your music on is something that is new. I mean, my generation had our Walkmans and Discmans, and there are some people that suffered hearing damage. This what we see in our schools now with cell phone use and earphones perpetually in people's ears is even at a higher scale than people walking around my high school with Walkmans. And so this is something that we're concerned about for the future. This is kind of my public service announcement. If you're somebody that listens to your music on super high all the time, please take this to heart. This has nothing to do with this course. I just don't want you to go deaf. I would love for you to hear the voices of your children when they talk to you for the first time. Well, maybe not your children, your grandchildren, okay? Try not to go deaf prematurely. All right. I put this onto the handwriting part of the note already, but I called it I0 just to sort of set it aside and make it be special in my handwriting. But here we go, that 1 times 10 to the power of negative 12 watts per meter squared, in case you didn't catch it before. That's the intensity that we're always going to be comparing our music to, or sorry, our intensities to. And I think that's as far as I want to go. Let's talk about what has to be done for homework, okay? So I'm going to put this in writing, but just to make sure that everybody has an idea of what's got to get done, I'm going to pull it up on the screen here. Remember, we've got a homework plan, we've got a workbook, and we've got a notebook. Hopefully you're using the notebook, but if you're not, that's okay too. I've also got some online quizzes for this unit, and they're not marked by me. I won't see the results, but if you like them for practice, I've linked them all there. If they don't work anymore, let me know. They're just quizzes that I had sort of set up or set up links for because students wanted to have something on the website to help them along with stuff. But let me know if they don't work anymore. The homework plan, let's go to that first. We're on topic 5, and right over here, topic 5, Oh, look, who's there? Who's online right now? Oh, Matthew McNaught. Who else was on here? I think I saw Max Chen earlier. Okay, so there are some questions here. Let me zoom in. You're going to be doing some. Oh, won't let me control the side to side slider. There we go. You're going to be working on pages 7 to 11 for reading, and then there are some questions in the workbooklet on pages 12 and 13. I would highly recommend that you do the reading in the workbooklet. In this case, our textbook is fairly weak on explanation, and so what I've had to do is go to a couple of other textbooks and cobble together something useful. Okay, so I went to a couple of other textbooks and basically wrote a few pages of textbook and included that in your workbooklet. So if you go into your workbooklet and you go to topic 5, you're gonna scroll through it or flip through it, and you'll see a little bit of a re-explain of what I've talked about here. It is worth reading through it. It is worth understanding it, and it'll work as a foundation with examples for going on and doing the questions that I'm assigning. The questions, of course, coming after this reading section, and you see it's like a little mini textbook section. There are 4 questions on in the first problem set, and there are 10 questions in the next problem set. There should be solutions posted for all, not full solutions, answers posted for all of them. So please check them out. If you have if there's discrepancies or if there's things that don't work out in the answers, let me know. I'll send out a how-to video, or I'll let people know about the typos. I think that that's everything that I want to talk about today, and I just hit the 1 hour mark. So, oh boy, what a video. Let me come back one last time. I really hope everybody's doing well. I'm only hearing from a few of you, like by email, and so I'm hoping that that means that things are going well for the rest of you. For those of you that I am hearing from, thank you very much for dropping me a line. It's nice to hear that there's somebody out there. And if there's anything I can do to clarify topics in this unit, let me know. This is going to be the only topic that we do this week because I think that it's something that deserves your attention for a week. Okay? What you're going to be doing is, like last week, submitting a photo of a single page of your work for communication purposes. All right. Hope everybody's well, and look forward to seeing you in the not too distant future, I hope. Bye.